In this lecture, we will describe space groups in the configuration space. Then we'll describe the Fourier transform of the configuration space. And that is how experimentalists actually see and understand lattices. What they actually see are irreducible representations of space group. So here is an example. This is a square lattice. And I will start this example, as usual, by defining a bunch of things. Space groups and their symmetry operations. We will follow Dresselhaus, so I'm using Dresselhaus numbers. Dresselhaus definition 18. Point group. And then we have to define translations on a discrete lattice. It's a group of operations which carry a crystal into itself, crystal into crystal. Together, point group and translations are called space group. For example, this square lattice, I can move it one lattice spacing down, I can move it one lattice space up to the left, two to the left, and if this is just a region of an infinite lattice, obviously a lattice set map into itself. I can turn it by 90 degrees. I can turn it again by 90 degrees. So these are so-called point group rotations. But if I try to turn it by some odd angle or continuous angle, that doesn't fit on the lattice. So that is not part of the point group. I guess I have to show you this. Found it in a lab in Hawaii. Theory, practice, and our lab, what actually happened. A bit of notation again. Pretty standard in the subject. Rotation by some angle alpha, and translation by integer vector tau in units of the lattice spacing. This is a group element of our group, space group. If I don't rotate and I don't translate, that's the identity operation. If I rotate by alpha but don't move the lattice, that's a finite group. In this case, it's called a point group, specific to crystallography. Let's keep orientation fixed and move by a lattice spacing or multiple of lattice spacing in every direction on our crystal. That's called pure translation. We can write this in a matrix form. We can write it as alpha and translation acting on a 1, 2, or 3-dimensional vector, and we will obtain another vector on a lattice. Convention is we take that vector and we rotate it by rotation by alpha. And then we add to it a translation, so we move the origin to some other point. So, what is the multiplication table for this group? Here is a Dresselhaus definition, 19. So if I first operate by alpha tau, and then by next translation tau prime, and rotation beta, the way it works is first you apply rotation to the vector, then you translate, add a vector tau, and then that's a new vector. You rotate it by beta and translate by the second translation. So that's the group operation. Theorem. All elements of space group G are of form pure translation from translation group, capital T, that's a subgroup of the group G, it's just translations. This translation group defines what's called Bravais lattice. Translation obvious, we take the crystal and we move it. And we move it in integer step in every direction. To be sure that it's a good subgroup, we have to show it's a self-conjugate subgroup. You might remember this from triangles. For triangles, rotations was a self-conjugate subgroup, but reflections were not self-conjugate because reflection would take you from one reflection to another. So it's self-conjugate or invariant or normal. How do you check this? Take an element and you act on it on the right by the inverse element. So this is just any element. You're acting by the full space group on the subgroup of pure translations. The first operation is rotation plus translation. Here I have to remind you how the multiplication worked. We first apply our rotation, then translation, and then on the result we apply the rotation, and then we add the translation to our problem. We have to be careful. We have to understand how the inverse works. Inverse says that inverse rotation is not a problem. We have to be careful because translations and rotations do not commute. Check it yourself if you don't believe me. So rotations are really not a problem. We first act on the translation and then we translate with tau. And then we do it one more time. And now I have to translate it in opposite direction. And now I have to do rotation on the inverse rotation, acting on tau. Plus rotation on this element we are looking at, that's tau. So you notice the first guy and the third guy cancel. So this is identity times a rotated vector. The vector that we started with was in a lattice, and rotation puts it into lattice. So we obtain another element on the lattice. So that proves that translation group is a normal or self-conjugate subgroup. The main nuisance here is you cannot write this just as a direct product of translation and rotations because those things don't commute. So consider pure translation by tau prime together with pure rotation by the point group and check whether they commute by applying them in one order and subtracting, applying them in the other order. So you get rotation by alpha. So this is what we get in one direction. Now do them in the other order. First translate by tau prime and then rotate. Rotation will be fine. There is no problem with that. First rotate and then you add the second translation. And clearly these are not the same elements, so the elements don't commute. That's fine. We know what to do with non-commuting groups. We have to do with something with Reddit already. We have to define a right coset. So we can use the right group by using just pure translations. So we take a pure translation and multiply it by any group element to define the alpha coset. Any element but fixed rotation alpha. So rotations look okay, and we get some elements. That's called the right coset. We can do it for every element alpha. Now let's do the left coset. It works the same. As the right and left cosets are the same, that means that the translation subgroup is a self-conjugate or normal subgroup. So that leads us to the theorem. The cosets C alpha form a factor group of the space group. In other words, a product of two cosets is the product of all possible group elements in the cosets. So all group elements that have rotation alpha in them and rotation beta in them. When you translate, rotations always multiply like this should. But then we get rotation on the second element. And when we run over all possible translations on the lattice, we get our finite point group. And that enables us to define a factor group, which is a finite point group, with translations quotiented out. And that group, with finite number of elements, because there's a finite number of cosets we will find, is a finite group of kind that we know. Now, what's a point group? Point group is a group that leaves at least one point invariant. That's why they're called point group. In your mind, what you're doing is you take a point, a site on the lattice, and you rotate the entire lattice. Discrete rotation. For example, if lattice is arranged on triangle, this transformation will now rotate the entire lattice. So, what are space groups? They're defined by rotation and a translation. Physically, the symmetry of the crystal will manifest itself through translational modes called phonons. This will be kind of smooth, long wavelength excitations of a lattice, sometimes called magnons, etc. Rotations, or the point group, are discrete. Typically, we'll see anisotropy. When you look at crystal in different directions, we will see different separations. For example, diamond looks different from a cubic lattice. So, rotations will define what's called natural phases. What translation group helps us it's a normal subgroup space group. So if you understand what one neighborhood does, we can generate the entire crystal by translations from it. Translation group works in a configuration of physical space distinct from momentum space. So Bravais lattice is a space of all possible translation in 1, 2, 3, or any number of dimensions. It'll be characterized by the unit directions. For example, in 2 dimensions, we have A, which is a lattice spacing vector. It's a little vector which is the shortest distance between atoms and the lattice. And then we can go to any integer lattice spacing. So n1 is the number of lattice spacings in crystal direction A1. Same in second direction. So that leads us to the notion of the unit cell. So for example, in 3 dimension, you'll have to specify 3 directions. I mean alpha, beta, gamma. And now it turns out the choices of these angles are very restricted. The simplest case would be to do the 1 dimension, but nobody understands it. So we'll write this always in two dimensions. So the simplest kind of unit cell is where the 3 lattice spacing are the same, and then we have a cube, or in 2 dimensions we have a square unit cell. These are the simplest examples of unit cell. That's the picture we started with. Now we can talk about things. So for example, trying to get the angles right is so restricted that in 2 dimensions there are only 6 what's called primitive different possible shapes. And if you have a unit cell, then you can tile the entire space by its copies. So, sometimes that's called a generating region, and sometimes we call that a fundamental domain. And unfortunately, some books mean by fundamental domain something totally different. So in square lattice, the unit cell is a little square, but I can slice it into smaller pieces. Now when I look at it, I can actually tile it by 8 copies of a smaller domain. So if you look at a fundamental domain, typically a fundamental domain in a crystal will contain some atoms. And particular disposition of atoms within fundamental domain is called a motif. So if you have a primitive cell with some motif, that uniquely characterizes the crystal. Every possible crystalline lattice has a fundamental domain, typically a square or a triangle or a hexagon. Now within it, there are details they call motif. It is this enumerations of motifs within fundamental domain that gives it classification of all possible crystals. In 3 dimensions, there are quite a few possibilities, but finite numbers. So crystallographers did this already at the end of 19th century. In 2 dimensions, these motifs called Wallpaper Groups. And you think of them as all possible kinds of wallpapers, which consist of little pieces with which you can cover the wall. These things exist for at least 150 years, and they have names, and they are tabulated, etc. The people called spectroscopists, and typical problems are in 2 dimensions you tend to have rotations. In 3 dimensions you tend to have a hedral group. I will not go into too much detail for that. There are tetrahedral groups, you know what tetrahedron is. And there are octahedral groups in 3 dimensions. You might not remember what octahedron is. This kind of notation is called, after a Dutch spectroscoper, Schoonfields notation. Then there is another widely used notation called Hermann-Mageun notation. Translationally tiled smallest bit by translation. You call those shapes primitive, but then you have to decide whether they're face-centered or corner-centered. That's what P and C means, corner or face. This, I'm afraid, gets increasingly more boring. This cell has some kind of symmetry. See where the reflection symmetry, rotation. To give you an example, our little naive square lattice with no features within it has a Hermann-Mageun notation, primitive cell 4, meaning it's a square, and then no reflections in both directions. So, various PMs, etc., tell you about symmetries. It's very boring unless you need to do it for a living, but here is an example when you can cover a square by reflections of a little triangle, 8 odd copies. So basically, it's a combination of 2 things we already know. We know discrete translation have to do with Fourier transforms. We know that these tilings around a point have to do with finite groups. But there is some trickery. It's not so easy. It's a little bit hard to say, why is this so weird, complicated. But basically, for Lattice, the natural thing is translation, which is we added stuff along that direction. But for rotations, we use multiplications. So it's slightly awkward, this way of understanding groups, but this is the way people have developed the technology. The most amazing thing is by the time you're done and you go to reducer representations, here it's called reciprocal lattice. What experimentalists actually see when they look at, let's say, graphene, they actually see the reciprocal lattice. So it's not a mathematical obsession, it's a physical fact. This dual space. You shine light or X-rays through crystal like graphene, and you look at the dots on diffracted light. Perfect crystals have a finite number of signatures in reciprocal space. And this is the amazing thing that enables us to shine light on millimeter scales and see atomic scale of the problem. It's rich and amazing, and it still goes on. If you join some of our labs,